Okay, so our topic is gravity. There are a couple basic equations that you should know. One is Newton's universal law of gravitation, which is Fg equals g, which is a constant. That constant is 6.673 times 10 to the negative 11th. That is times m1 times m2 divided by r squared. M1 is going to be what's at the center, and then M2 is going to be what's orbiting M1. The other equation is the potential energy for gravity, and that's going to be potential energy equals negative G times M1 times M2 divided by R.
Using these two equations, you can derive four other equations, the first one being acceleration due to gravity. We know that Newton's second law is F equals ma. So we know that the force due to gravity is G times m1 times m2 all over r squared is equal to m2 times g, which is the acceleration due to gravity. And then the m2's cancel out, so you're left with g equals the gravitational constant g times m1 all over r squared. And then the second equation is that you can derive is for velocity. Once again, you're going to use FMA. So you have g times m1 times m2 over r squared is equal to m2 times a. Now you're gonna change the a to the acceleration, centripetal acceleration. So you're gonna get the same g m1 m2 over r squared equals m2 times v squared over r. Now you're going to solve for the v, so you get g times m1 times m2 times r all over r squared times m2, and that's going to equal v squared. The m2's will cancel out, and then the r's will cancel out, so you're left with 1 at the bottom. So, and then you take the square root, so v equals the square root of g times m1 all over r. The third equation is for the period, and this is okay, so we know that centripetal acceleration, so the g that we found earlier, is equal to 4 pi squared r over t squared. And we found what g equals earlier, so we plugged that in. So gravitational constant g times m1 over r squared is equal to 4 pi squared r over t squared. Now we're going to solve for t squared. So you get t squared is equal to gravitational constant g times m1 equal to 4 pi squared times r cubed. And then, so once again solving for t squared, so t squared is equal to 4 pi squared r cubed all over gm1. This is like Kepler's third law, which is t squared equals k r cubed. So the 4 pi squared over gm1 is the constant, and that's how you get that. The last equation is escape velocity. So, and that has to do with energy. So you have the initial kinetic energy plus the potential energy equal to the final kinetic energy plus the potential energy final. You know that the final kinetic energy is 0, and so is the final potential energy. So you take that, you know, kinetic energy is equal to 1/2 mv squared, which is equal to the potential energy that we know, so gm1 times m2 over r, and that's normally negative, but since to get to the other side it becomes positive. And then now you're solving for v, so you get v squared is equal to 2gm. The m2's cancel out again, so that's how you get the m there. And then all over r, so v is equal to the square root of 2gm over r. This is m1. And those are the 4 equations that you need to know.
Okay, so now we're going to do an example problem. The planet Mars has a satellite Phobos, which travels in an orbit of radius 9.4 times 10 to the 6 meters, with a period of 7 hours and 39 minutes. It asks us to calculate the mass of Mars from this information. Now, this is an example free response problem, and if you remember when you're taking the test that we derived the equation up here for when we have the period and the radius, and we're trying to solve for the mass of Mars. So we know that t squared is equal to 4 pi squared times r cubed over g times m1. So m1 is what we're trying to solve for. So we can just rearrange all these variables to solve for m1. So we end up, we multiply by g, and then you divide you multiply by gm1, and then just divide by the t squared divided by g. You end up with m1 equals 4 pi squared times r cubed divided by t squared times g. So then after that, it's just as simple as plugging in the radius and plugging in the period. Before we plug things in though, we need to make sure that we have everything in the correct units. The radius needs to be in meters, which it is, but then the period needs to be in seconds, and we have it in hours and minutes. So it's just a simple calculation to find out how many seconds 7 hours and 39 minutes is. So you do 7 hours times 3,600 seconds per hour, and that equals 25,200 seconds. and we have to calculate the 39 minutes part. So 39 minutes, there's 60 seconds for every minute, and that means that there's 23,000 or 2,340 seconds. And you have to add those two together, and we end up with a period of 27,540 seconds. So now we can plug that all in, and we end up with m1 being equal to 4 times pi squared times the radius, which is 9.4, times 10 to the 6th meters cubed, divided by the period, which we found was 27,540 seconds, and that's squared, times g, which, like we said before, was 6.67 times 10 to the negative 11th. And the units on that is newtons times meters squared divided by kilograms squared. So then you just solve for that, and you end up finding that the mass of Mars is 6.48171 times 10 to the 23rd kilograms. Okay, so then another example problem. This is more of a multiple choice question, although we don't have answers as multiple choice, but an Earth satellite is orbiting at a distance from the Earth's surface equal to one Earth radius, which is about 4,000 miles. At this location, the acceleration due to gravity is what factor times the value of g at the Earth's surface. So what we're going to be doing is comparing the force of gravity at the surface. So the radius will be equal to just r, because we're going to end up canceling the r's out anyway. And it's going to be versus the satellite, the satellite, which is at a radius equal to 2r, because it's an additional 4,000 miles above the surface, so 4,000 plus 4,000 is 8,000, and if r is just 4,000, you're going to end up with 2r. So we know from the equations we derived earlier, we know that g is equal to g times m1 divided by r squared, and that applies to both. But for the satellite, it's going to be divided by the quantity 2r, because the r is indeed 2r for the satellite. So we end up with the same thing on both sides. So g equals m1 times m1 divided by r squared, but then the satellite is g equals g times m1 divided by 4r squared, because 2 squared is 4. So the only difference between these two is a factor of 1/4, which is seen by the 4 on the bottom. So we know that the factor is 1/4.
Alright, so the next problem we're going to do says, if a planet has a radius 20% greater than that of the Earth, but has the same mass as the Earth, what is the acceleration due to gravity at its surface? So, we know that the radius of the Earth is equal to 6.38 times 10 to the 6th meters, and the mass of the Earth equals 5.98 times 10 to the 24th kilograms. In this problem, the other planet has a radius 20% greater than the Earth's, so we multiply this number by 1.2 to get the new radius of the other planet, which ends up equaling 7.656 times 10 to the 6th meters. And it says that the mass of this other planet is the same as Earth, so we already know that value. So we need to find acceleration due to gravity at this other planet. So using the equation that we derived earlier, saying that the acceleration due to gravity is equal to g times m over r squared, we can find the acceleration due to gravity. So we just plug the numbers into this equation. So g is equal to the Constant G, 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared times the mass of the other planet, which is the same as the Earth, so 5.98 times 10 to the 24th kilograms. And this is all divided by the radius of the new planet, which is 7.656 times 10 to the 6 meters, and that's squared. So we calculate that all out, we end up with the acceleration due to gravity being 6.805 meters per second squared. And that's all.